you will have sort of a chance at redemption in one way. And what do I mean by that? I mean, this material in chapter 9 does not hinge greatly on chapter 7, 6, 7, and 8. Right? And to tell you the truth, chapter 9, how should I say? It has the least calculus in it of all the chapters we do in Calc 2. If it's any consolation, most students find Calc 3 easier than Calc 2. Not easy, less difficult than Calc 2. Anyway, so the formula we're applying is this up here in the corner, right? And what we were playing with here is we were adjusting indices. Notice this only works when you start at 0 and you got r to the n. Here we start at 0, but we don't have r to the n. Right? Here we start at 0, we don't have the n. Here we don't start at 0 and we don't have n. Okay? And so you've got to learn to shift these indices so that you can apply the formula, and you you add and subtract things to compensate. You add and subtract stuff to compensate. All right. So what do I need? I'm going to do things one thing at a time because I'm a rather simple individual, right? Yes. Okay. One thing I need is I need it in here. How do I get it in there? Are you ready? I've showed you. And leave some space there. Okay. All right. I need it in there. What do I do? I'm going to multiply by I'm going to multiply that by that. Now look here, look what happens. N minus 2, multiplied by that to the 2, those add together, you get an n. See, we got the n that way, right? But I have to compensate now. So out here, this is a 1 over 3 squared. So out here I put squared. I effectively multiplied by 1. Never underestimate the power of multiplying by 1 or adding 0. But and it's good to think in those terms because you've got to think that if you change something, you compensate something. So I change the value here, here. So this is going to be that's to the end now. Now, what's the next thing I got to do? I got to make that n equals 0 at the bottom. You could have done this first, by the way, if you wanted to. Might be easier, I don't know. So let's see. That sum there is going to be 3 squared times, I need some brackets, because I'm going to do sigma n equals 0 to infinity. Why did I put a 0 there? Because my formula up here that I'm going to apply, this is the only formula I have for geometric series, and it requires a 0. So I put a 0 there. But I have to compensate for that because by putting a 0 there, I am adding a term to that series. It's going to have 1 extra number. So I'm going to subtract. subtract. I added the 0th term. I'm going to subtract the 0th term. Right? Now, by the way, 1/3 to the 0 just equals 1, right? But I put it as 1/3 to the 0 so that you can see that I added the 0th term to the sum, and I'm subtracting off what I added here. So never underestimate the power of, in the green, multiplying by 1, and in this red and purple, I'm adding 0. Adding it here, subtracting it there. Okay. Smile. I know what you're saying. Mr. Miller, I can't smile in calculus. Smiley's not allowed in calculus. So this is going to be 3 squared. What's that? 1 over 1 minus 1/3. That's what that is. That's 1. Right? 1 over 2/3 is 3/2. 3/2 minus 1 is 1/2. I'm going to move stuff around a little bit so that the slide doesn't go down so far. All right. What was this problem about? The problem was about making this fit the formula. For that to fit, we need a 0 there, we need an in there. So I chose to take care of the in up there first. You could have chosen to take care of the 0 first. You put a 0 there and subtract off the 0th term, just like I did. You get the same answer. But here, so I made that into an in by multiplying by those two, and that produced an in right here. That's what I needed. The next thing I needed, so I put the 1/3 in there to this 2. Those exponents add to n, which is what I want, and then I compensate out here. Now I'm stuck with evaluating this. And in order to do that, I need to put a 0 there. So that sum right there is this in parentheses, in brackets here. I added a term there. In fact, I'm going to make it purple. I added the term there, subtract it off there. Now I can apply my formula to the sum. 1 over 1 minus 1/3. It's 1 over 2/3, 3/2. That purple expression there is just a 1. Questions? There you go. One almost exactly like it. Almost exactly like it. Right? Too easy, right? Now, what I don't want to do is I don't want to have to put like 6 of them here, right? Because you need to be doing more than just this one. And it will do the most good if you do this one tonight. I'm not kidding. This afternoon, this evening, that's when you need to do this, when you hear my ugly voice still rattling around in your head. When you look at this in a week, get behind homework, you look at this stuff in a week or so, you're going to be going, oh, yeah. Properties of infinite series. We've kind of been using these, but the sum of a constant times a sequence, you can bring, basically you can bring the constant past the series sign. It's, by the way, these are the same as for limits. That's the easiest way to say it, right? You can bring any factor. That C is a factor in there. You can bring past the summation sign, right? And so you bring past the summation sign, and in this sigma ANs go to A, becomes C times the sum of A. The series of a sum is the sum of the series. Series of a difference is the difference of the series. We're going to be using those. We've already done this one, right? Now, I paused when I put this up a couple days ago because in my years of teaching this, students get wrapped all around the axle on these 2 principles here. What I want you to understand, these 2 theorems are the same theorem. No, one's 9.8, one's 9.9. Well, that's true. But I'm going to introduce you to a principle, right? Let's call this P, and this another statement Q. Okay. If P, then Q. In math, we say that as P implies Q. I can never have P without Q. Can I have Q without P? Okay. If the guy hits you the baseball, you catch it in the air before it hits the ground, he's out. If he's out, did you catch it? Not necessarily. There's other ways of getting a batter out. But if you catch it in the air, he's out. So if you catch the ball, then the dude's out. But if the dude can be out other ways, he can take a third strike, right? He could get thrown out at first, right? He could say something to the about his, never mind. All the things that baseball players say to umps, right? Okay. All right. Okay, so what is this? If a P, P is this series converges. Now let me give you a little lesson in logic. If something doesn't converge, it diverges. Either converges or diverges. So this is not P. That little squiggle in logic means not. And here this says the limit of the nth term goes to 0. That's Q. This is the limit of the nth term not go to 0. So that's not Q. Let me give you a little, if this is called a statement, I'll tell you what, I'm going to call it, I'm going to do it simple. I'm going to call it, it's an implication. This is called the contrapositive of that implication. You don't have to know this. You have to know how to use it, though. Here's the punchline. A implication and its contrapositive are logically equivalent. Means they're the same. So, for example, I have this pen. I have this pen in my hand. If I let go of the pen, it will fall. If an archangel comes up and tells you the pen didn't fall, what do you conclude? Then I didn't let go of the pen. Because if I let go of the pen, it'll fall. They're the same statement. If then, if it doesn't fall, I didn't let go of it. So when you negate the conclusion, P implies Q, you negate the conclusion the pin didn't fall. That implies I didn't let go of it. Those two are logically the same. So these two are the same theorem. I belabored that too much. I mentioned that if you have the limit of the nth term, if it goes to zero, if the series converges, the nth term has to go to zero. Because if it doesn't go to zero, suppose it goes to 1, then you're going to be adding that 1 infinitely many more times, and it's not going to converge. So if the nth term doesn't go to 0, there's no way it can converge. It diverges. Now, note, you already know this. That's what I've been saying. Notes 1, they say exactly the same thing. 2, if the nth term goes to 0, that does not imply, oh, wait a minute here. Whoa, 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 whoa. That's a typo. We have a big typo here. Yeah. If the nth term goes to 0, that does not mean the series converges. It does not mean the series converges. Now, you remember the other day, we left off. Let's see here. Right here. This is a discussion we were having on this slide. If this converges, then the limit of the nth term goes to 0. Is the converse true? If the limit of the nth term going to 0, does that mean it converges? The answer is no. Now the question is, how about this one here? Sigma 1 over n. 1 plus a half plus a third plus a fourth plus a fifth and so on. The nth term, this goes to 0. Does that converge? Eventually, you're adding 1 millionth, 1 million and 1th, 1 million and 2th. You're adding just minuscule amounts. Does that converge? Right. That was a major, major problem in math for a while, long while. Right? All right. Next section. We got some open questions there. We have some open questions. But we're going to be using these principles all over the place. And the big principle that students get mixed up with is they get these mixed up with number 2 here. That if the nth term goes to 0, that it has to converge. That's not going to be true. It could converge, but it doesn't have to converge. That's like saying if the batter is out, you could have caught his ball in the air, but you don't have to. There's other ways for a batter to be out. Integral test of P series. Here we're going to have a little bit of calculus, but nothing like we've been having till now. Ready? We have a series. We have a series. And AN is some formula in N, right? AN equals some formula. If we make that formula a function and integrate it, this series and that integral from 1 to infinity both converge or both diverge. They sink or swim together. Right? They both converge or both diverge. So right here. I haven't talked about a P-series yet. This is the integral test. All right? But we're going to use it to get something called a P-series. Remember we had the P integrals? Yeah, that was at the end of chapter 8. Yeah, okay. End of chapter 8. Oh, while I'm at it, I just want to make sure we announce in here again that the final exam is Wednesday, the first day of finals, 9 to 11 a.m. Right here.
What day is it?
The 28th. The 28th. Right? Tuesday night, they usually have a ice cream social. And I think they got COVIDed out last year. But they usually have an ice cream social before in the CAF the night before finals start. All right, that's a Tuesday night. I'll be there. It's the only time you're seeing this fat boy on campus past 10 o'clock. Okay, right? That's it. It starts at 10. It starts at 10. Man, at 10 o'clock, I am cutting some serious Z's, man. I am never up. Okay. But me, your loving fuzzball professor, will be in the CAF, and I set up shop on usually the north side of the cafeteria, which is the side of the building formerly known as the library. Right? So I set up shop over there with some tables. I usually come early and invite students from all my classes. And in fact, I invite any math student on campus. I don't know if they're in my class or not. They're in Dr. Kite's differential equations class. Bring it. You know, I should be able to handle the rest of it, right? They're in the class across the hall. Some kind of remedial class. I don't know which one that is. Bring it, right? Any math student on campus can get help. Also, the night before that is a Monday night, which is Spark. So Fat Boy is going to be on campus Monday night from 8 to 9, and then from Tuesday night from 10 till 10:03. No, just kidding. From 10 till I've been there past midnight before, but usually just chatting. 10 to 11, 11:30 a few times. All helping students, okay? All right, so you'll have the exam the next morning, so you'll have some help available the night before the exam. All right, I will, we don't care. I don't really make an effort to have office hours during the finals. So I'm grading finals, and I'm looking to get my finals out of the way. All right, because I want to get on with my summer, right? Okay, so here, P series. If P is bigger than 1, sigma 1 over into the P converges. Wait a minute. Use the integral test to show this. Well, to use the integral test, we look at integral from 1 to infinity, 1 over x to the p dx. Remember this? The very end of chapter 8. Near the end. Wasn't the very end. It was close to it. P series. This, you remember these two either converge or both, these both converge or both diverge. It says If P is bigger than 1, prove that this converges. This equals 1 over P minus 1 if P is bigger than 1. Right? By this theorem. So that integral converges for P equals 1. Therefore, converges for P greater than 1. So if you know the P integral test for integrals, this is a P series. A P series with P larger than 1 converges. Show it. Now, in this bottom example, use the integral test to show that diverges. Well, it's the same thing. Integral 1 to infinity, 1 over n to the P. Did I say n to the P? X to the P? Yeah. One over x to the P. Dx diverges if P is less than or equal to 1. That implies that the series n equals 1 to infinity, 1 over n to the P, diverges for P less than or equal to 1. So we can use a lot of our properties of integrals, and especially the improper integrals. Because notice, I'm going to come back to this slide. This integral test involves an improper integral. By the way, an extension of this is that if n goes to 2, if n is 2 to infinity, it's the same thing here. You go 2 to infinity here. It's not going to matter because 2 to infinity, 1 to infinity, you're adding or subtracting one term. So if it's finite, if that integral exists, plus or minus one term is still going to exist. So here, adding, here, this is what I just said.
Can you go back, please?
Oh yeah, sorry. All right. Done. There you go. Adding or subtracting finitely many terms does not change whether or not I should say a series, converges. Yeah. By the way, if there's ever ways to make the slides more clear like that, tell me. Right? Tell me, because sometimes I get blinded by the fact that I'm not the one learning from my slides. Right? I'm not the one learning from my slides. You guys are the ones I want to understand it. And if you guys have a way to make it clearer, I'm going to take your word for it, pretty much. Okay. Okay. So if a series beginning at 0 converges, it will still converge if n starts at 23. Right? Because those first 22 terms, they just equal a number, right? You add up 22 things, it's just some number. And so if this converges, if I subtract off the first 22 terms or 23 terms or however many, it still converges. The same thing happens. If this diverges, if this sum diverges, if I start at the 273rd term and add up from there on, that will still diverge. The first 273 terms are some finite number. If all of them grow infinite, if I subtract off 273 terms, it's still going to be infinite. So in improper English, infinity minus a number is still infinity. If it diverges, it's going to diverge plus or minus any number. Right? And by the way, this little double arrow means if and only if. If that diverges, so does this. If you can show the tail of a series is infinite, diverges, then that series is going to diverge no matter where you start. What's happening? You know what is happening? Well, I'm afraid it's going to happen. Here we go. It's that spatial time. We're on slide number 48. Okay. Convergence of a p-series. We just showed this using the integral test, right? This, that, converges if p is bigger than 1, diverges if it's less than or equal to 1. Right? So I added these two things in there. It doesn't matter if it's greater than 0. If it's less than 0, it diverges even faster. Okay. All right. So yeah, you're going to hear a lot. Blah, 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 equals this series, which diverges as a p-series with p less than or equal to 1. Or such and such, such as converges as a p-series with p bigger than 1. We're going to have a lot more tests for series here coming up. A lot more. And they're all going to blend together. They do. More than as much as any other chapter. You've got to keep up or this just becomes a blur. The techniques, you can't distinguish when to apply one or the other. We're gonna do this. Remember this guy? This is called the harmonic series. This is the one I showed you a second ago into the slide. And mathematicians worked for probably a couple of thousand years on this. I know way back in the time of the Greek mathematicians, Euclid, right? Apollonius, those guys, they were working on stuff like this. And they didn't know whether this converged or diverged. And what they did is they started adding up terms. And what they were looking for a number that sum never went past. If they could show that it never went past 50, then they showed it converged. They haven't shown what it converged to, but they would show it converged. Well, the problem was any number they pick, when they added up enough terms, they could pass that number. Yeah. So they never, but it just looks like it converges. Well, this is a p-series with P equals 1 implies diverges and that is amazing. Now you remember what I said a second ago. If a series diverges, you can lob off the first million terms and the terms after those million terms, the sum of those terms will diverge. It grows infinite in the tail, in other words, not the first finitely many terms. The first finitely many terms will always be a finite quantity. So that means if I started this series at 1/1,000,000th, plus 1/1,000,000th and 1, plus 1/1,000,000th and 2th, plus 1/1,000,000th and 3th, those are tiny, tiny, tiny numbers. And then I go out to a 1/1,000,000th, 1/1,000,000,000 and 1th, 1/1,000,000,000 and 2th. That some of those will still grow infinite, which just amazes me. I mean, that really looks like it should converge, right? Now let's do it using the integral test. The integral test says, we look at this, the integral from 1 to infinity of 1 over n. Let's do 1 over x. We got a problem, Houston. We have a problem. What is the antiderivative of 1 over x? The antiderivative of 1 over x.
X to the -1. Or not.
Well, this is x to the -1.
X minus 2. divided by
That's the
2.
derivative. You take the derivative, you'd go -1 x to the -2. The integral, if you wanted to do the antiderivative that way, you would add 1 to the exponent, divide by the new exponent.
I was gonna say that was.
Yeah. This screws us up. The antiderivative of this isn't that. This is the only number it doesn't work for, is -1. The antiderivative of that, lady and gentlemen, is natural log. So we have this infinite bound, though. How do you handle infinite bounds? Well, back to section whatever that was. One of the last sections, it was this. You do the limit as k goes to infinity, integral 1 to k, 1 over x dx. That's how you did it. That equals what? Natural log, limit, k goes to infinity, natural log of x from 1 to k. That's going to be limit. K goes to infinity. Right? Oh, look at that. I got an M with 4 humps there. 4 humps on my M's. You think a guy named Mark Miller would write really good M's? Not true. Fake news. Natural log K minus natural log 0. Natural log of 0, not actually 0. No, you nincompoop. Natural log of 1, which equals 0. And the natural log of k, as k goes to infinity, remember what the graph of natural log looks like? Looks like that. It keeps going up forever. So this is infinite. Right? Which implies that sigma that diverges by the integral test. I'm always going to make you say why something diverges or converges. Because a chimpanzee can flip his banana peel and say whether, and pick converge or diverge, it'd be right half the time, right? And are you smarter than a chimpanzee? Sometimes I'm not. I'm just going to keep it real, folks. I make stupid mistakes sometimes. All right. So yeah, that's a good one. This is one that I was going to. Let's see how long this is. Going to skip in the interest of time. This
is the checkers game where grandson and granddad will bond. This is the kitchen. So I'd like to talk about 3 infinite series. So
9 minutes. I'm going to kill 9 minutes on this. I hope you like it.
1 plus a half plus a fourth plus an eighth plus blah, blah, blah. What's that? And the answer is it's 2. This is the problem of Achilles and the tortoise. Achilles is 2 stadia, or whatever the unit of length is in ancient Greece, from the tortoise. Well, after a while, Achilles gains on the tortoise 1 unit, and so the remaining distance is only 1. Then after a while, Achilles gains half of the distance to the tortoise, and now the distance to the tortoise is a half. After a little while, Achilles gains another 1/4 of the distance to the tortoise, and so on and so on and so on. The story, according to Zeno's paradoxes, is that Achilles never catches the tortoise. Well, of course, Achilles never catches the tortoise at any of these times, but if you just wait a little longer, Achilles will have caught the tortoise. The total length that Achilles gains on the tortoise is 2, and that's why this is true. Now let's look at 1 plus a half plus a third plus a fourth plus a fifth.
This is the harmonic series right here.
7 plus an eighth, and so on, and this never ends. How big is that? What is that? What I mean is if I stop after many, many, many terms, so I'm adding some huge finite list of numbers. How big is that, and what happens when I add more and more and more? And the answer is this is infinity. Why? Well, let me group the terms. Here's the first one. Here are the next 2. Here are the next 4.
This is another way of showing.
Would end with 1/15, and this goes on forever.
This sum does.
Yes.
Without counting.
I'm always told that's not a number, right? Well, so what exactly does this mean? You give me any number at all, 50 trillion, and I can stop this series and say, okay, I will only go this far. I'm adding only a finite number of numbers together. But that sum will be more than 50 trillion. That's true not only for 50 trillion, but for any number you name, no matter how big. And that's what it means that the sum of the series is infinity.
So it's blowing up. It's like
Exactly.
It's getting away from us.
Exactly. We say that the series diverges. So let's look at the first term. Well, it's 1. Thank you. How about these next 2 terms? Well, you know what? This one is bigger than a half. Each one of these terms is bigger than a quarter. A half is bigger than a quarter. A third is bigger than a quarter. And there are 2 terms. So this is bigger than 2/4, which is again a half. How about these 4 terms? They're all bigger than 1/8, and there are 4 of them. So if I add these guys, it's bigger than 4/8, which is a half. If I look at the next 8 terms, they're all bigger than 1/16, and there are 8 of them. So the sum is bigger than 8/16, which is a half. If I stop far enough, this sum will be more than a half plus a half plus a half plus a half plus a half, and I can go on as many times as I like, accumulating 1/2 until I get to more than 50 trillion. So sooner or later, the sum of these numbers will be more than 50 trillion. The catch is that I have to go enormously far out in order to do it. But let's not worry about that.
Long way out.
Okay, never mind just how enormous. Let's leave it there for this sum, which has a name. It's called the harmonic series. I'd like to explain how to use the harmonic series to stack dominoes. Well, actually, I don't have dominoes in my office, but I have lots of issues of the annals of mathematics. Oh, yes, I have lots and lots and lots. So we're going to use copies of the annals of mathematics as dominoes. Let's just take 2 of them first. If I move this one here, it's going to collapse. But if I move it so that its center of gravity is Let's see if that works. I'm being a little conservative. The center of gravity of this guy is sitting over that guy, and so it does not collapse. Now let's take these two and put them very carefully on top of the third one, taking care that the center of gravity of this whole guy is above this issue of the annals of mathematics, and therefore, this looks precarious. Okay, there, it does not collapse. And now perhaps I could put these three on top of the fourth, and if I succeed in doing that, I will not tempt fate. I will just declare that, that we have succeeded. Look, so let's see, how are we doing? It hasn't collapsed. Looks a little flaky. It hasn't collapsed. How far can we make this guy stick out? Suppose that I have all those copies of the Annals of Mathematics, or perhaps all the copies of the Annals of Mathematics ever printed from the beginning of time to the end of time. Wonder how many that would be. Anyway, we have all of them, and we stack them up, and we demand that the file cannot collapse. Well, this is merely paper, so sooner or later it takes too much of a load, it will be crushed, but never mind, these are imaginary rigid dominoes. Can we ever make the top guy so far out that it is not resting on the bottom guy at all, that this edge is not lying at all over this book that has come out farther?
Further after the bottom book.
Exactly. And the answer is, oh yes, in fact, you can make this pile come out in that direction as far as you like. Because if you look at it, if you have any copies of the Annals of Mathematics and you do an absolutely perfect job in an ideal world, the distances that they are slid out from one another are in the proportions 1 to 1/2, to 1/3, to 1/4, to 1/5, to 1/6, and so on, to 1/n, if there are n copies of the Annals of Math, or n plus 1 copies of the Annals of Math. And so the fact that the harmonic series diverges tells you that you can eventually make this pile come out as far as you like. Because 1 plus 1/2 plus 1/3 plus 1/4 plus and so on, if you stop way, way far out after a gazillion for a large enough value of a gazillion, will be more than 50 billion. And therefore, this distance out there will be more than 50 billion times the height of the Annals of Mathematics. All right, let's put the Annals of Mathematics aside. Now let's do the same thing to the series 1 plus 1/2 squared plus 1/3 squared plus 1/4 squared plus, going squared, blah, blah. Now let's try to do the same thing. We're going to take the first term. All right, so that's 1, thank you. Let's look at the next two terms. Now, this is 1/2 squared. This is smaller than 1/2 squared. So we've got two terms, and they're each smaller than 1/2 times 1/2. So that's smaller than 2 times 1/2 times 1/2. That's smaller than 1/2. Let's look at the next four terms. Here they are. They're all 1/4 squared or smaller. So they're smaller than 1/4 squared plus 1/4 squared plus 1/4 squared plus 1/4 squared. There are four terms there, and so these guys together are no bigger than 4 times 1/4 squared. That's 4 times 1/4 times 1/4, and that's 1/4. So this whole thing is less than 1/4. If I looked at the next 8 terms and played the same game, I would find that that's less than 1/8, and so on. So now look, if I go out to a gazillion terms, I'm guaranteed that what I've got is less than 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus something or other. I stop at 1 over some power of 2. Hey, wait a minute, remember first result. This series never, the sum of these guys is never more than 2. The sum of all these numbers is 2, and the sum of the first gazillion numbers will be slightly less than 2. So therefore, I'm guaranteed that no matter how many terms of this guy I take, it will be less than 2. So it doesn't run off to infinity the way the harmonic series does. And in fact, you could wonder, what is the value of the sum of all of these terms? And that was a famous unsolved problem of the 18th century. And the answer is pi squared over 6. Pi creeps in where you would least expect it.
Isn't that cool? Pi
I
creeps
was
in.
exactly here, this place, and I was having an interview, and then the phone rings.
Why pi squared to the
Hello?
6? Why?
The voice was saying, hello.
It's a really advanced result. It
Our
took,
world is divided, and to fix it,
that's a really advanced result, way beyond us, way beyond me. But it like he said, it took mathematicians a long, long time to solve that. Very, very complex. That one is. But pi comes up in really interesting spots. Anyway, back to here. I've worked 9 minutes. Oh! Converge or diverge? Ah! We only have 4 minutes. A good teacher would let you go. We're going to do this one. Integral, 1 to infinity. In fact, we're going to do 2. because that's what they. And if you put 1 in there, you have log 1, which is 0. So that's why they start at 2. Whoever they is. I always like when teachers put that. I don't know. They might put that on the test. They? Who's this they, Kimasabi? Who's they? Right? So 1 over x square root what do we do? Well, we're going to rewrite this in the interest of time. One thing is when the time is of the essence, I don't have time for pop quizzes. Rewrite it that way. Does that help us? I think it does. Why do I think it does? Is let this be U, and then let this be du. Right? All right. And that's going to be integral 1 over square root u du. All right. What's that going to be? We still got the bounds to deal with. So u is natural log of x, right? X equal 2. That means u is log 2. X equal infinity implies that u is 0. Well, whoa, hey, I'm sorry. Infinity, sorry. Because if x is infinite, u is infinite. So this is going to equal from log 2 to infinity. Well, this right here is u to the minus 1/2. How do I integrate that? Add 1 to the exponent, divide by the new exponent. So that's going to be it's going to be that. Add 1 to the exponent, u to the 1/2, divide by 1/2 from log 2 to infinity. Now, we haven't dealt with that infinity properly. This 1/2 on the bottom becomes a 2. So that's going to be 2 limit if k goes to infinity, u to the 1/2 from log 2 to k. Log 2 is just a number. That's 2 limit k goes to infinity. K to the 1/2 minus log 2 to the 1/2. That is infinite. Therefore, integral 2 to infinity, 1 over n square root log n. Sigma, I mean sigma, sigma, sigma. Diverges by the integral test. So the integral test brings all of our knowledge of integrals to bear on series. We'll leave it there. Do we have a homework here? Oh, we don't. We got, oh, look how many examples we're doing. Oh, you know what I need to do? I need to turn a couple of these into homework. I'm going to turn some of these into homework. In fact, right now,
Can you go back, please?
yeah, I'm going to turn a couple of those into homework.
Oh, sorry.
Yeah. Because I don't have a homework in there, and I'm doing too many examples. Right? See ya on Monday. See you in an hour. 10 minutes. She has to put up with me 2 periods in almost in a row. Before and after lunch. Yeah, I'm going to turn some of those into homeworks. In fact, we're going to turn, oh dear. All these are P series. I'll figure out. All right, see ya.
Enjoy the movie.
You've been watching the MLB or